Huh?
Dit zal u het onreine zijn onder het wemelend gedierte dat op de grond wemelt. De mol, de muis en alle soorten padden. De gekko, de hagedis, de varaan en de chameleon. Deze zullen u onrein zijn.
It's amazing how rapidly they can attach and detach the feet. Just milliseconds from full swing to being attached completely. They're so dynamic. You know, if you were looking at this animal from above, you'd think it was running on the floor, not on the side of a polished perspex surface. The gecko is pretty sticky. So I'm pulling here. I don't want to hurt the animal, but it can move this big plexiglass plate around quite easily. So one gecko here can lift probably a kilogram's worth of weight without injuring the animal. So to pull it off of a wall is quite difficult. And how they manage to be so sticky is a problem that has really fascinated scientists for well over a century.
So we're interested in discovering the principles, the ideas about how you can grab onto any surface, and then trying to transfer that information to engineers to try to inspire them to build not only new adhesives, but adhesives that maybe could someday be used on a robot. In particular, we like to think that someday you could make a robot that could undergo search and rescue, so that find individuals in earthquakes or in fires, or they're trapped as a result of some terrible accident. And you could have a swarm of these robots going anywhere, climb up the sides of walls, and find the individuals very quickly.
There are 850 different kinds of geckos, and each one has a different type of foot. In fact, taxonomists classify geckos primarily on the structure of their feet. This one is pachydactylous. It's a broad, thick toe. Yeah. It's just amazing. How can they stick to such a smooth surface? One of the first hypotheses was that maybe the geckos have little suction cups in their feet. That turns out not to be true, that their little toes can stick even in a vacuum or underwater. Another hypothesis was maybe they have little microscopic hooks, but as you can see, it can stick to the smoothest of surfaces. Another possibility is that perhaps there's a thin film of liquid in between the gecko's foot and the surface, and the geckos stick by capillary action, like many insects do. But if we lift up the gecko's feet, we can see there's no footprint left behind.
We're also looking to ants. They use a glue. They have claws that can grab on when it's rough, but a pad that comes out and sticks on very tightly with glue so they can maneuver on different surfaces. So here's the foot of an ant. Here's the pad pulled back in. And that, when it comes out, it secretes the glue and then grabs on. And you can see that. The animal's here running upside down. And there are the claws. It's a flat surface so they don't grab in. And the pad comes out. And it sticks by the pad. That's wet adhesion. That's very different from what we see in the gecko.
Well, on the bottom of its feet, you can see that there are little white strips, and each one of those strips is actually a brush of about 20,000 microscopic hairs, and that's the sticky part of the gecko's foot. Well, it's well known that the geckos had these microscopic hairs, but what wasn't clear was what the mechanism was that makes the hair sticky. I mean, after all, our hair isn't sticky, or at least not, hopefully not. But the gecko's hairs are incredibly sticky, and we wanted to know how that works. Well, what we found was that geckos stick by this incredibly weak force. This was really a surprising result. They stick by a force that's called van der Waals force. And these are forces that happen just when two surfaces get very, very close. So what's happening here in the gecko's toes is those millions of hairs have thousands of smaller tips on each hair. And those smaller tips are so close to this surface that they actually bond at the quantum atomic level. Now, these millions of microscopic tips are able to get so close to the wall that they literally become one with the wall at the quantum scale. Each one of those atomic interactions is quite weak. Billions of them together can be extremely strong. You might wonder, how is it that the gecko can get all of these hairs off if they're so incredibly sticky? And we discovered that when the angle that this hair makes with the surface increases, these little tips begin to peel off. You can see that in the toes. They peel their toes up from the tip first. They have the most double-jointed toes in the world. They can curl them up like this. You know, and obviously I can't do this with my real finger, but they curl them up just like you would peel a piece of tape off the wall. It attaches so gently and detaches so easily that you can imagine using it for applications like nanosurgery, where you might need to pull on a blood vessel or a nerve very gently and not do any damage.
Oh, yeah. So we study the locomotion of a variety of different animals with many legs. That's why we're called the Polypedal Lab. We study things like this giant cockroach. We look at centipedes and millipedes and animals like scorpions and also geckos. We take the animals and we put them on treadmills. Here's a small one, a miniature treadmill. And then we run it and we try to look at their motion of their legs and their body. So we actually have a special treadmill called the gekko mill that we can put the animal on to watch it move up. What's really surprising when we looked at this diversity of animals, that 2, 4, 6, 8, and even 44-legged runners all seem to move the same way. They all bounce along like a pogo stick, despite the fact they look totally different. That single idea then can be used to make very simple, effective robots. This is named Rex, the robot hexapod, built at the University of Michigan and McGill University. And it runs in the field very much like you see insects and geckos and even dogs or you. It bounces along as it's running in the field. This is the Rex going over a pipe. Doesn't see anything, doesn't feel anything, no brains, just goes over that surface because it has legs. One of the reasons nature doesn't use wheels is because there aren't roads. But what it can't do yet, and that's the next step, is to be able to climb up surfaces. So we're studying the adhesive of the gecko because it's really special, and we want to add that to designing the feet of the next generation of robots.
That's pretty much it. That's the process we have so far for making the synthetic gecko hairs. So what we made so far is our very first prototype array of nano hairs. In this region here, made of silicone rubber, is approximately 1 million small bumps. Each of these bumps, we found, has about the same adhesion as the nano bumps on the real gecko. So this is our first steps towards building the synthetic gecko array. But you need an electron microscope to see them.
So this is it?
So this is it. So we have a lot of work left to go to make these hairs have a lot more functionality, but it's very encouraging results because the first bumps we made, they stick very well to glass and they give a pretty decent adhesion. These are one of our first engineering models for the tips of the toes of the gecko hairs. The real stuff, so having something which we think would be as good as a gecko, is probably about 3 or 4 years away.
We've done some work with a company called iRobot, and they've made a robot they call the Mecho Gecko that uses a glue, but successfully peels from the surface. They were able to get a robot to climb up a wall. The problem is that it uses glue, not like the gecko. And the glue gets dirty very quickly, whereas the gecko can self-clean, although we don't know quite how it does it yet.
Yeah, they're quick. Well, if this gecko had tape or any other kind of adhesive on the bottom of its feet, it would be done for. But they clean themselves off quite easily. The adhesive doesn't seem to attract dirt. We don't know why they're self-cleaning. We have a few ideas, but we're working on that this summer.
We're about 5 years away from having a robot that has claws and toes and then these hairs so that it should be able to go on any surface. 5 years for sure. Maybe sooner.